All right, so welcome to a beautiful snowy winter day here in Tahoe. For those of you outside the area, we did get a nice little storm, which was very much appreciated. We like our snow up in the mountains. But anyway, today our plan, as always, is to go over any kind of questions you guys have about what's been going on. But we're going to continue our discussion of applications of integration, things that we do with them. I want to show you one more area problem, just a little twist to it that will make things a little bit easier if you can spot it. So I want to show it to you. And then we're going to move on to the next application. And this one's going to be volumes. We're actually going to look and see how we can use integrals to help us find volumes. And it's probably not a surprise that we can do that. If we find area by adding up little areas, we're going to find volumes by adding up little volumes, but we'll get to that in a minute. So before I dive in, are there homework questions? Anything you guys would like to look at, talk about? Okay, so 7, 8, and 14, and 10, all from 2.1. All right, we got all kinds of area questions. So 9 and 10 from 2.1. All right. So it looks like 2.1 is the section of the day, huh? All right, so I've got 7 through 10, so 7, 8, 9, and 10, and 14. Now, I don't know that we're actually going to do all of those, but we'll at least take a look at them. All right, so let me go ahead and share my screen, and we'll go take a peek at those. I'll ignore my mail. Hold on one second. Get to assignments. There we go. So 2.1. Oh, and big news. I got a new computer. You may notice that this is like flying, pulling up nice and quickly. I'm so excited. My old laptop was like 10 years old, so it's about time, right? I am that guy that like uses things till it dies and then finally gets a new one. Like my car right now, it's a 2004 Corolla that has 189,000 miles. So I'm hoping I can make it to 200,000, and then when it craps out, well, then I'll worry about it then. Anyway, all right, so let's take a look at this guy. So it says the shaded region between the graphs of y equals minus 2x squared plus 20 and y equals 3x minus 15 is displayed below. All right, so you see that? So it says what we want to answer here. First, it says the shaded region lies between which x values. So we're going to need to figure out what are the x's that form the left and right boundaries of this thing. And then it says the typical rectangle is shown in here. What's the height of the rectangle in terms of x? So that means we want a formula. We're going to want a formula for that height that's in terms of x. And then we want to find the actual area, which means doing the calculations, right? Actually going through and doing the integral and getting those values. All right, so that's our plan. Let's see what we can do. So let me go ahead and write these down so I can go to the whiteboard so I know what functions we're dealing with, and then we'll go from there. All right, so to the whiteboard. So those two functions, again, were y equals minus 2x squared plus 20, and the other one was y equals 3x minus 15. So we'll go ahead and draw that kind of shape again. Oh, goodness. Hold on a second. Let me erase that nonsense. See if I can draw it actually relatively correctly. That's better. All right, so it did something like, there was the parabola, and there was our line. I know I'm not quite right vertically, but we're looking for something like that. All right, so first things first, we got to figure out the boundaries. So what was the deal with those? How did we find boundaries before when we wanted to find the area between two curves? If they weren't given, what do you do?
Make them equal.
Yeah, we set them equal. We're just looking for the intersection points. So we'll take minus 2x squared plus 20, and we'll set that equal to 3x minus 15 and solve it. So it's a quadratic. So I'll move everything to one side. So the minus 2x squared, bring that over, make it positive 2x squared. And then when I subtract 20, I get minus 5. All right, so we need to solve this quadratic. There are lots of ways of doing that, but I recognize that this thing factors to 2x plus 5 times x minus 1. If you don't see that, that's cool. You can use the quadratic formula, complete the square, do whatever you need to. But then we set those factors equal to 0, and so we get x equals minus 5 halves from the first one, and x equals 1 from the second. All right, so we now know these numbers. Okay, this one's the minus 5 halves, and that one's the 1. So when it comes time for us to do our integral, it's going to be an integral from minus 5 halves to 1 for our bounds. All right, so basically all these boxes and things on this homework, they are just walking you through the steps, right? Like one of the things we have to figure out are the bounds. So they're just having you enter those in the box on the way. All right, anyway, so there's our minus 5 halves and 1. All right, so now the next part said, let's figure out what the height of the rectangle is in terms of x. So the height of the rectangle is going to change, right? Depending upon where we are. Like here's one of them. Here's another one, right? So depending upon where we are, those rectangles have different heights. But we always get those heights the same way. So when you find the area between curves, how do you get the height of the rectangle?
Subtract the higher function from the lower one.
Yep. So we're going to do top minus bottom. That's the way I like to think about it. So top minus bottom. So the top function in this case is the parabola. So minus 2x squared plus 20. And then we're going to subtract 3x minus 15.
Good for phone internet.
All right, so if we distribute through, we get minus 2x squared minus 3x plus 5. So this is what's going to go into that second box, right? It said, give us the height of the rectangle in terms of x. That means as a function of x. There you go. Okay, so that's what goes into the second box. And of course, when we go to do our integral, pardon me here, I'm trying to move a window. I've got too many windows open on my screen. This is what's going to go inside our integral. It's going to be the 2x squared minus 3x plus 5, and then dx. So again, this one is just trying to prompt you to do the pieces. So there are bounds. This is the thing we're integrating. And I'm going to leave this one here. You know what to do at this point. We're going to use the power rule on those, then use the fundamental theorem, plug in 1, plug in minus 5 halves, which will get us the area. All right, so there is basically what needs to happen for this guy for problem number 7. All right, so cool, questions? We good? All right, so let's go ahead and go check out the next one. So number 8, we're going to hold off on number 8 because that's the one I want to show you the trick on. All right, so let's look at number 9. So number 9 says we want to find C such that the area of the region enclosed by parabolas y squared equals x squared minus c squared, and y equals c squared minus x squared is 210. All right. Well, let's see how we're going to set that guy up. So let's go back to the whiteboard. Let me go ahead and clear this old drawings, and we'll do some new ones here. So let's start with, what do the graphs of these things look like? Right? Because if we're going to talk about the area between them, it's probably helpful if we kind of have a picture so we know which one's on top, which one's on the bottom, where the bounds are, what, you know, all that sort of stuff. So let's start with x squared minus c squared. So if c is a constant, right, this is just going to end up being like y equals x squared minus 1, y equals x squared minus 100, like whatever. X squared, that's a parabola. It's a happy parabola because it's positive, so it's going to be a smile. The minus c squared, what does that do? What does that do to our smile? Like if I had, say, y equals x squared minus 1, what does the minus 1 tell you to do?
Move it down 1.
Okay, so we're going to move it down 1. So this one, we're going to move it down. How far? Well, we're going to move it down c squared. Okay, so here's the first one where this is minus c squared. Right? So we move it down 1, we move it down 100, move it down 36, whatever. That's just telling us we're going to move it down some. Okay. It's a sad parabola, so it's going to be a frown. And this c squared is positive c squared. Okay, so the region that we're looking for is this egg-shaped region. So just letting you guys know, my computer just blinked up that my internet connection is unstable. So if I lose connection here, everybody sit tight. I will reconnect and get back as soon as possible. Okay, I froze for a couple seconds. That makes sense. One of the bonuses of living in snow area. All right, so we good? We see what we need to do. So let's think about what we want. We want to find the C so that this area is 216. So here's what I suggest. I suggest we figure out what the area is using the integral. It's going to be in terms of C, and then we can find C. So let's approach this the same way we did the others. Let's first figure out where do these actually intersect. All right, well, if we're going to figure out where they intersect, we're going to do the same thing that we did before, which was set these guys equal to each other. So we'll take x squared minus c squared and set that equal to c squared minus x squared. Moving things around, I get 2x squared equals 2c squared. So x squared equals c squared, which tells me that x is plus or minus c. So these places where they come together are at positive and negative c. So notice that I'm doing the exact same thing that we did before. I just don't have actual numbers here, so my bounds end up being in terms of that letter. So here's where the area is going to be then. The area, we're going to integrate from minus c to c. We're going to take our top function. The top function was the sad one. So c squared minus x squared. And we're going to subtract from that the bottom function, which was the happy guy, x squared minus c squared. We're going to integrate that with respect to x. All right, so before we actually do the integral, let's simplify in here. I've got c squared minus a negative c squared, so that's 2c squared, minus x squared, minus another x squared is minus 2x squared. And now let's integrate. All right, so the 2c squared, that is a constant. I'm going to warn you about this because this is going to happen sometimes. You're going to see this letter and you're going to go, okay, cool, that's c cubed over 3. But it's not, because c is not our variable. Our variable is x. That's why it's really important to have this differential in there so you know what the variable actually is. So c is a constant, which means 2c squared is going to give us 2c squared x, right? It's the same as integrating 2 or 50 or whatever. You're going to get that many x's. This one, though, does become 2/3 x cubed. So we add 1 to the exponent and divide. And now let's plug in our bounds and see what we get. So if I plug in c, I get 2c cubed minus 2/3 c cubed. And then I'm going to subtract from that. Well, when I plug in negative c, I'm going to get negative 2c cubed, and then plus 2/3 c cubed. It's a plus because the negative cubed is negative times negative is a positive. Watch, your signs are going to give you trouble sometimes with these, since we're subtracting and subtracting negatives and blah, blah. All right, so just watch those. But let's see what this ends up giving us. So we have 2 plus 2 is 4, minus 2/3 minus another 2/3. So this is 4 minus 4/3 times c squared. And I believe that becomes 8/3, if I did my math correctly here. Or c cubed, not squared. All right, so what we've just figured out is what the area of that region is. It's 8/3 c cubed. You tell me the c, this is the area. All right, well, now we're ready to actually figure out what c is, because we were told that we wanted this area to be, what's it, 216. All right, so that means c cubed is going to be 3/8 of 216. Does that go in? 27 times, oh, nice. So 27 times 3 is 81. So that's c cubed equals 81. So c is going to be the cube root of 81, which I believe is 3√3, or 3 cubed root of 3. So if we want that area, this area right here, to be 216, we have to make sure that c is 3 cube roots of 3. All right, so if you think about this, we did exactly the same thing as the other one. We started by figuring out the intersection points, right? So we came over here, we set them equal to each other, we solved for x. Then we used those bounds and did the top minus bottom to find our area. It just was in terms of that c. But having this was perfect because then we could set it equal to the area we were looking for and find our c. So it started out exactly the same. There was just that little wrinkle at the end. Oh boy. All right. So there was number 9. How are we feeling about that one? And it's okay if we're feeling not so great about it, because that's a tricky one, right? There's a lot to that in order to get it solved. All right, much better now. I will definitely take that. I like better. All right, so that was number 9. And then on my list, I still have I think it's 10 and 14, if I recall correctly. So let's go take a look at number 10. All right. So number 10, there is a line through the origin. Okay, there's a line through the origin that divides the region bounded by this parabola and the x-axis into two regions with equal area. What is the slope of that line? All right. Well, let me go ahead and write this guy down here real quick. 5x minus 2x squared. And let's go to the whiteboard. So I don't know if you're anything like me, you read something like that and you go, I have no idea what that means. I don't get it. It's too many words. I find that I need the picture. So let's start with the picture. So we've got this guy right here. We have the parabola 5x minus 2x squared. Okay, so that's a sad parabola. I see that it's got a y-intercept of 0. There's another x-intercept that's out at 5/2. So it does something like, that. I think is a little bit better. Shoot, if I erase, that's gone. Let's try that again. Okay, so that's the parabola, right? Looks something like that. All right, now what it says is that there's a line through the origin that makes the region bounded by the parabola and the x-axis two regions with equal area. Okay, so basically what we're looking at there is we're going to take a line through the x-axis or through the origin, and it splits it so that the area on either side of the x-axis is equal. So we'll make one of them red and make one of them blue. And that's what we're looking for. All right, so before we even attempt this, are you guys cool with the picture and cool with what it's asking us to do? Because that's super important, right? We have to know exactly what we're doing before we can actually do it. All right, so Eric just says, I think it's talking about above the x-axis. Let's go back and look at it again, make sure we got it right. Okay, so there's a line through the origin that divides the region bounded by the parabola and the x-axis, into two regions. You are correct. Man, I was going to answer a completely different question. All right, so it says divides the region bounded by the parabola and the x-axis into two regions with equal area. Thanks for catching that. Mine was going to be way more exciting. All right, well, let's change this picture. So hold on, we're just going to clear it. Get rid of it. Let's start over. Okay, so there's that. We've got our parabola that does that. And then we've got our line through the origin that does that. And the two areas that we want equal are this one and this one. Okay, thanks, Eris. Thanks for catching that. You are definitely right that that's what it should look like. All right, so Yeah. What are we going to do here? What are your thoughts? Here's what I would do. I would look at what's the area of the red, and then figure out what's the area of the blue. Do those two separately, and then I would set them equal to each other. So that's what I recommend we do. So let's start with the red. Let's think about calculating the red area. So I'm going to do that in red. So we're going to need an integral. All right, we'll worry about bounds here in a second. Well, actually, I know the lower bound is going to be 0 because that starts here at the origin, since both these graphs go through the origin. The upper bound is going to be whatever this value is, right, where they come together. So we'll have to play that trick where we did, like we did last time, where we set them equal to each other. And then we're going to have to do top minus bottom. So the top for this one is going to be 5x minus 2x squared. And then we're going to have to subtract the bottom function. Well, here's the thing. I don't know the equation of this bottom function. I know it's a line, right? I know it's y equals mx plus b. I do know that it goes through the origin, so b is 0. But I don't know the slope. And in fact, that's what I'm trying to find, right? I'm trying to find the slope of the line that makes this so that I have two equal pieces. So I'm going to have to just leave that as mx. Okay, but that's what we're going to be integrating, top minus bottom. Now, we still have to find this point where they intersect. So let's do that. We're going to take those two equations and set them equal to each other. So we have 5x minus 2x squared equals mx. So I'm going to move some things around. So I have 5x minus mx is equal to 2x squared. And then I'm going to divide everything by x. Now, normally this is trouble, potential trouble. You don't like to divide by variables, but I know I'm going to be okay because the only places this would be bad is if x is 0. And I'm not worrying about that point. I'm worrying about this other one. I just think it's going to be easier to do this than factoring. So this leaves me 5 minus m is equal to 2x. So x is equal to 5 minus m over 2. So that 5m minus 2, or 5 minus m over 2, is going to be my upper bound. So if you told me what the slope was, I could plug that in for m, and then I'd know exactly what that point is, but this is the generic. Okay, so I'm going to put dot, 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 because at this point it's a matter of integrating, plugging in. It's going to be algebra yuck. I'm just going to tell you, it's going to be algebra yuck. But you guys are at a point where you can suck it up and deal. You don't want to, I know. But you can handle that. All right, so that's going to get us our area for the red part. So then we want to set that equal to the area for the blue part. So let's start looking at that one. Okay, so for the blue, same story. We want to do top minus bottom, right? And we still want to have our bounds, right? Now, here's the thing with this guy, and I don't know if anybody caught it. Let's zoom in on that blue part. So there was the line, and then there was the parabola that was coming down. Okay, so that's the blue area. That's this piece. What functions on top and what functions on the bottom? How about we start really easy? What's the function on the bottom? What's the equation of this line right here?
Would it be 0?
Yeah, it's y equals 0. So the bottom function is 0. We're subtracting 0. We don't have to subtract. This is what you learned as integral, right? It was the area under a curve above the x-axis. So this one, we don't actually have to do a top minus bottom. We just integrate the top function. Okay, so I'm going to go back to my original question then. What's the top function? All right, so Alexi just said the line. And that's true sometimes. Because sometimes the line isn't the top function. Sometimes it's actually, sometimes it's the parabola, right? Sometimes it's that 5x minus 2x squared. Because
in this case, would we want to integrate with respect to y?
We could. Spoiler alert. Yeah, we'll talk about that in a second. But let's just think about, if you can't see from the little picture, I've got a big shit-eating grin on my face. Because check this out. Here are the little representative rectangles. And notice that sometimes it's on the line and sometimes it's on the parabola. So for this one, if we say what function is on top, the answer is it depends where we are. Because sometimes it's the line that's on top and sometimes it's the parabola. And where it switches is right here at that intersection point. So here's what we would actually have to do. For the blue, we're going to have to do this in two pieces. The first one is going to be from 0 to 5 minus m over 2 of mx dx. That's the one where we've got our line, and we're going to go out to 5 minus m over 2. But then we'd have to add on to that another integral that goes from 5 minus m over 2 out to this intersection point, which was the other intercept for the parabola, which was 5/2. If you set it equal to 0 and you factor it, you'll see the other one is 5/2. So that guy's going to be 5/2. But now the function that we're integrating is the 5x minus 2x squared. So this one kind of sucks. I don't know about kinda. It sucks because we have to split it into two, right? If we set it up this way, the problem is the top function switches somewhere along the way, which makes this a little bit more difficult to do. All right, but we got it. We can definitely do these, right? Do some steps. We'll get our value. And basically what you're going to want to do once you're done with the integrals, you're going to have a formula for the red area in terms of m. You're going to have a formula for the blue area in terms of m. And then you're going to set them equal to each other because we wanted equal area. And then solve for m. All right, so this guy's a doozy. This is another one that requires quite a bit. And I know you don't like having these letters in here. I know you don't like it. You'd much rather it just be a number. Tell me the line is y equals 2x. And then everything's numbers. However, that is one of the things as we progress in math. We try to be more and more general. So just realize that it is a number. It's just a number you don't know yet. So it behaves like a constant. It does everything like a constant. You just got to get comfortable with it. Okay, so I don't remember who that was that chimed in earlier and said, is this one where you'd want to integrate with respect to y? Who was that? Who wants to fess up to that? It's all good. No one wants to admit it. All right. Well, somebody.
That was me. I had typed it
Okay.
in the chat box.
Okay, cool. Thanks, Rigney. I guess I just didn't see it. Oh, there it is. All right. So Rigney said, isn't this one where maybe we want to integrate with respect to y? Now, this isn't what this is the thing that was the holdover that I still wanted to show you. And you can actually make these integrals a little bit easier sometimes if you change your perspective. All right. So I'm going to clear this so everybody saw it, everybody's good, everybody's got what they need. And let me show you how we could look at this slightly differently and still make this work. So when we set up areas between curves, right? So here's one curve and there's another. We always looked at it vertically, right? We said, let's build our rectangles vertically, add all those guys up, and we're going to get our area, right? But there was nothing that said we had to do it vertically, right? Nothing at all. So if I have some shape here, I could have instead thought of it as, what about horizontal rectangles? If I were to split this into a bunch of horizontal rectangles instead of vertical rectangles, and then go ahead and add them all up, I'm still going to get the same area, right? There's nothing that says these rectangles have to have set widths and variable heights. We could have said, what if they've got set heights and variable widths? It's really the same thing, right? We're just changing our perspective a little bit. We're looking at these things from a different angle, literally. Okay, well, if we do it this way, think about what's going on. So let's kind of go to the approach that we did before. And I'm going to start with not area between curves, but let's look at just an area with one curve. So here's something, right? And let's say we were looking at a horizontal piece to this. So we're looking at, say, this area right there. So let's build it kind of the same way we did before. We're going to now partition the y's instead of the x's. In each of those partitions, we're going to build a rectangle whose height is determined by the curve. Right? And then we're going to add all those rectangles up and then do an infinite number of them. Okay, so here's what this is going to look like then if we kind of change our perspective. We're still going to have a limit as n goes to infinity. We're still going to have a sum that goes from 1 to n. The sum from 1 to n, that was the adding up all the areas. The limit was making it so we got an infinite number of them. But now let's think about the size of these rectangles. So we need widths and heights. Well, the heights, these are all going to be the same, right? Those heights are going to be now delta y instead of delta x, because it's just a little y chunk instead of a little x chunk. All right, so we're going to have over here a delta y sub I. And the heights are going to be determined by this thing. We now want it as a function of y, though. So I'm going to say, let's just say that this is g of y, meaning instead of solving for y, instead of y equals, it's x equals. And so the height then is going to be given by g of y sub I. I guess that's the width of the rectangle. But notice it's the same thing. It's base times height. Base times height. All right, well, if you take a limit, notice that this structure is exactly the same as what we saw before, except y's instead of x's, which means this is going to be an integral. Well, go ahead and say we're still going from a to b. But this time it's going to be g of y dy. So you can easily do the same kind of thing that we did before by looking at it sideways. So instead of dx's, you have dy's. Instead of x bounds, you have y bounds, right? So if we want to go to areas and looking at it sideways, it's still going to be a subtraction like we did before. But now it's not top minus bottom because that doesn't make sense. But let's put another function in here. All right. So let's say we're looking at just this area. If I want the heights of the rectangles, instead of top minus bottom, it's going to be right minus left. All right, so if we're looking at this in terms of y, if we go between curves, we're going to do right minus left. And that's going to give us the width of those rectangles, and the heights of those are all going to be the dy. Okay, so this derivation, exactly the same derivation you saw before. We're just turning our heads sideways. It just means we need our functions in terms of y instead of x. So if we go back to that picture, no, I'm not going to clear everything. Let me just erase. So let's go back and look at that region that we were trying to do for that second integral. And what it looked like was something like this. So we had the right. So we were looking at sort of like a pizza slice kind of shape. So this was our line and this was our parabola. So when we did it vertically, like we were used to, it meant we had to do two different integrals. But if we look at it horizontally, now when we build these rectangles, we think about it this way, notice that the right side is always determined by the same thing. It's always the parabola. The left side is always the line. So again, since we want the area to be right minus left, this is only going to require one integral. And what we would need then is to take those equations and solve them for x instead of y. So turning yourself sideways can definitely help make it so that you only have one integral instead of two. We just have to look at it in a slightly different way. Okay, so let me show you what I mean. Not with these, or well, yeah, let's use this shape, but I'm going to put some specific numbers. I don't want to do the y equals mx and all that because that's a little bit too confusing for right now. So let's do this one. Let's look at come back here, and here are going to be our equations. One of them is going to be 10 minus x squared. Okay, so pretend that that's a decent parabola. That's y equals 10 minus x squared. All right, and then we're going to take a line through the origin again, but let's go specifically with y equals x. So y equals x is going to be right here. And I want to look at the region that's down here, okay? Let's find that area. So it actually has the same kind of shape. It's got a line and then a parabola. So if we were to do it vertically, we'd have to split it into two. All right. Well, instead, here's what we're going to do. We are going to solve both of these for x, so that when we're looking in this region, we can think about them as functions of y. So this one, solve for x, already is y equals x, x equals y. The other one, though, when we solve that, this gives us x squared equals 10 minus y, or x is equal to the square root of 10 minus y. So when we go and we set up our integral to find this area, it's going to be the square root of 10 minus y minus y dy. And again, this is right minus left. In this region, we think horizontally, right? The right side is my red line, or my red curve, which was the parabola, and the left side is my line, the blue curve. All right, so we still need to figure out our bounds. Well, our bounds now are on y, so we need to know how far are we going up and down to get this region. Well, the lower bound is going to be 0, right? Because that's the bottom of this. And then the upper bound is going to be at this intersection point. So you would take 10 minus x squared and set it equal to x. Right? Or alternatively, you could take the square root of 10 minus y and set it equal to y, either way. But you would solve this thing for x. Now, I chose a horrible, I just made this up, and I think I got a horrible set here because that does not factor. So you'd have to use the quadratic formula. We're going to get gross looking numbers here. Let's see. So you're going to get -1 plus or minus the square root of 1 plus 40 all over 2. So -1 plus or minus the square root of 41 all over 2. We obviously want the positive one. So the upper bound is going to be -1 plus root 41, not 91, 41. Sorry about that. Let's try that again. -1 plus square root of 41 all over 2. It's our upper bound. Okay, so this is a horrible number. That's because of what I chose initially. But the whole point of this is now we can just do one integral instead of two. And sometimes that's easier. Now this one's actually not easier. We don't actually know how to integrate the square root of 10 minus y. We don't have a way to do that yet. So actually you do. You could do a u sub. But it's going to be ugly. It's going to be gross. However, we did trade two integrals for one. So just keep that in mind, that when you're looking at something like this, you can always turn yourself, like change your perspective, and it can make it easier. If we go back to the original, I recommend you just do it as the two vertically, because trying to solve that quadratic equation for x, or that parabola for x, is going to be ugly. It's going to give you something really ugly that you have to integrate. So I would just do it vertically, although this is definitely a case where turning it sideways could make it easier. All right. So I think I've beat that one to death. There's still one more I know that was floating out there. Can someone remind me, was it 14? Am I remembering correctly?
Yeah, it was 14.
Okay, thank you. All right, so let's look at 14 here. So window has the shape of a parabola above a circular arc. Find the area of the window. Okay, so this is a good old top minus bottom kind of thing, area between curves. However, I wouldn't do it that way. I would actually use geometry. I would help myself out, because here's the deal. Trying to do the integral with the circle is going to be really, really tough. Let me show you why. I'm going to go back to the whiteboard and clear all this garbage. Okay, so think about the equation of a circle. X squared plus y squared equals r squared. We need to solve that for y. Okay, well, y squared is r squared minus x squared, so y is the square root of r squared minus x squared. So even if we have an r, let's put in a number like 1, for example. So we're looking at a unit circle. imagine trying to do the integral of the square root of 1 minus x squared. So right now, your best bet is to do a u substitution. The u sub doesn't work. And then you look at that and you go, oh, but it's a difference of squares. Maybe I do a inverse trig. Well, no, because the inverse trig needs to be a 1 over. Right? This thing, we don't have the ability to integrate. Yet you have to learn a new technique called trig substitution. However, we do have the ability to actually calculate that. Right? So let's think about it. This is a semicircle. That's the bottom side of our window, right? Is this semicircle? Oh, except it wasn't a semicircle, was it? It was just a circular arc. Yeah, we can still do this. I'd still use geometry to do it. Because here's the deal. This thing is just a portion of a circle. I know its area. Even if it was just a circular arc, we know how to find that area. I don't know if you remember this, but it's 1/2 r squared theta, or that guy's our theta. So we have ways of actually calculating that area, because otherwise it could be a little bit tricky setting this thing up with algebra, but it's exactly the same idea. So let's go ahead and set it up with the algebra so you can see it. I'm going to just real quick grab that information again. So I've got 11.3, 4.75, and 11.4 radius. All right. Sorry about that delay. I just needed to go back and get some specific numbers. So, all right. So here's what we've got. Let me clear these drawings again. So that picture looks like there's a parabola, and then that's a circular chunk. So in terms of numbers, I've got that this is 4.75. I've got that distance is 11.3. So let's start there to get the equation of the parabola. So that's a sad parabola. It's been shifted up some. I'm just going to say it's been shifted up. A. No, let's not call that A. Hold on. So I've got a sad parabola. I'm going to put minus a squared because it can extend out a bit. And then plus c. All right, well, here's what I know. I know the c is 4.75 because my vertex is brought up that far. So this tells me this is y equals minus ax squared plus 4.75. I also know the y-intercept, or the x-intercepts, right? On our axes, we can draw some axes here. So that tells me that this is going to be the point 5.65, comma 0. Because that's half of the 11.3. So I can plug that in over here. And notice I can solve that for A. So A is going to be 4.75 divided by 5.65 squared, whatever that number happens to be. But this now gives me the equation of that parabola, which is good. I need that, right? Without the equation of that parabola, I can't actually calculate this. All right, now I need to do something similar to find the equation of the circle. All right, so in order to do that, let's go to the generic equation of a circle. So the generic equation of a circle is x minus h squared plus y minus k squared equals r squared. And here's some things I know about it. I know its radius. They told us that. For my problem, it was 11.4. I know the center of the circle is somewhere on the y-axis. So that means the y-coordinate of the center is 0. So that guy's just going to be, or whoops, wrong one. The x-coordinate, sorry, is going to be 0. So it's going to be x squared plus, and I'll still leave it as y minus k squared because I'm not really sure what the k is yet. Okay, but I can actually figure out what k is by using this same point. So this guy, the 5.650, is on my circle, right? So I can take that and plug those in down here. So I get 5.65 squared plus y minus 0 squared equals, or sorry, not y minus 0, 0 minus k equals 11.4. So that tells me that k squared is equal to 11.4 minus 5.65 squared. So k then is just going to be the square root of that. So it's going to be the square root of 11.4 minus 5.65 squared. So now I know where I'm located because this is going to be the point 0, k. Just make sure that you pick the negative k, right? Because this one, it's a plus or a minus. So I'll go ahead and put a minus out here since I know we're down below. But once I get these numbers, I know everything about both of these functions, which is going to let us start filling in all of the answers. So let me go back to show you this guy again. All right, so it says, so find the distance from the x-axis to the top of the circle. That's that distance right here. Well, you're going to know what your k is. That was that distance, so you're going to subtract that from 11.4. So write the equation of the circle, we got it. Write the equation of the parabola, we got it. And so then the last thing is going to be find the area of the window. And again, you've got a couple of choices. One, you could do the area under the parabola and then subtract off this circular chunk, and you can use geometry to do that. Or you can solve those two equations for y, take the parabola minus the circle and integrate that from minus 5 point, whatever that was, 5.565, I don't even remember, right? But to the plus 5.565. And there you go. So you have a couple of different options at that point, but I'm going to turn you loose on that on your own because we need to keep moving. So keep working on that one. We can definitely look at it again, say on Friday, if people are still curious or are still having trouble. But again, the key was to find the equations using that information. So it was a lot of algebra, a lot of stuff we have to remember from before. Like everything that we've talked about so far, no calculus, all algebra. That's why these are hard. It's because of the algebra. Okay, well, we've now spent an hour going over homework, which is fine, but we definitely do need to move on. So I'm going to hop up to the whiteboard because I want to start showing you how we do volume. So I'll be right back with you. All right. So let's look at how we can use integrals to help us find volume. Think about what we did when we tried to find areas. We took a region, we split it into areas that we knew we could calculate, right? Rectangular areas, and then we added them all up to get our total area. Well, we're going to approach volume the same way. We're going to take a shape and we're going to break it up into a bunch of volumes that we know. And then we're going to take those volumes, add them up, infinite number of them, and that will give us our total volume. So the real question is, how are we going to split things so that we have volumes that we can easily get? The way that we do that depends. There are actually multiple ways that that can happen. And it really just sort of depends on what the structure of our region is, or our volume is. Give me a second here. The sun just came out, of course, and is kind of blinding the screen. So hold on one second. I'll trade the big glare for just a little glare from the light. All right. So how are we going to do this? Well, the first major way that this is done is with slices. All right. So I'm going to write here volumes by slices. And literally what we're going to do is we're going to take a shape, a volume, and we're going to slice it into a bunch of thin pieces. Now, to show you what I mean, I brought a friend, and let me introduce you here to Darth Vader. You all know Darth Vader, right? The Dark Lord. Well, this is actually a puzzle. It's a three-dimensional puzzle that's actually made up of slices. Now, I don't know how well you can see it. If I zoom in a little bit, you can kind of see down here the little like ridges of this. So it's not exactly smooth. If you kind of look at it from the side, you can kind of see the chunkiness here, right? It's a little chunky. But Darth Vader here is actually made up of a whole bunch of slices, and I'll show you. I'm just going to pull a couple off the top. Right? So now he's got a flat head. But what it's made out of are these things. You can see they're really, really thin chunks that have, some little bit. But when you stack them all together, so this is actually what, 5 slices. But you put those 5 slices together and you're starting to see some volume, right? Well, you take those 5 slices and add them to the other like 100 slices. And the next thing you know, you've got a 3-dimensional shape. Okay, so this is exactly what we're doing here. We're going to take a shape and we're going to slice it into a bunch of little thin wafers. Each of those has a volume, right? Think about let me pull another one of these back here. Hold on one second. Okay, so think about this thing. It does have volume. It's not a lot because it's thin, but if we wanted to find that volume, it'd be its thickness times its area, right? Area times thickness. Like that's how we figure out the volume of, say, a cylinder. You take the area of the circle and extend it out a little thickness. So all we really need to know is this cross-sectional area. If we can calculate that cross-sectional area, we multiply by a little thickness, that's going to give us a volume. So we'll take the volume of this slice, add to the next volume, next volume, next volume, next volume. So we had a sum of volumes. And then we're going to make it so that we get an infinite number of infinitesimally thin slices. So that's the approach we're going to do today. We're going to look at how do we do this if we just slice it infinitely thin. All right, so that's the process with this. We're going to slice into an infinite number of pieces. The volume is going to be the cross-sectional area times thickness. Right? So we're going to figure out what that surface area is and multiply it by a little thickness, and then we're going to add it up. All right, well, this is why the integral is coming in, because we're adding up an infinite number of things. And so what that integral is going to look like, going to be integral from A to B of the area times the thickness. The thickness, though, is going to be our differential. It's going to be our dx or our dy. It's that little tiny piece. All right. So think about this now. It's very similar to what we did before. But before, instead of adding up areas, we added up heights. Remember when we integrated, it was f of x dx, and that f of x was the height? Integrating the height led to area. Integrating area is going to lead to volume. So whatever the shape is, we have to figure out the cross sections so that we can then add this stuff up. So let's start with an example. And we'll start with kind of a, well, this is an easy one to do. This is an easy one to do mathematically. It probably doesn't seem like the easiest shape, but we're going to find the volume of a cone. Okay, we're going to actually find the volume of a cone. But this cone, I'm going to design it so that we've got some nice, easy equations to do. But I'm going to put the cone on its side, just for the sake of, I think it'd be easier for us to visualize this. But this is our cone. All right, now let's specify a little bit about this cone. Let's say that this cone has a height of 10, and it's got a radius that's also 10. All right, so no, I want radius. Yeah, we'll go radius 10. Make life easy for us. Okay, so both of those guys are 10. So imagine slicing through that. If I were to slice through this, what would the cross sections look like? What shapes do those cross sections have? Can you picture it? All right, thanks, Alexis. They're going to be circles. Right? I mean, you kind of see it at the bottom of that cone. It's a circle. Right? If you were to slice anywhere else, it's going to be a circle just of different size. So these slices are all circular. So there's going to be a smaller circle there, a bigger circle, a really tiny circle. Right? But no matter where we slice this thing, we're going to get ourselves a circle as the cross section. So let's start thinking about setting this up as an integral. I'm mostly going to do it in words right now, but we're going to integrate from somewhere to somewhere. But we're going to have our circle area times our differential. And the area of a circle, we know, is pi r squared. But here's the deal with those circles. Those circles, their radius changes. Right? The biggest one is actually going to be a radius of 10 when we get to the very, very end. The smallest one is actually a radius of 0. We think of that point that's at the very nub of the cone. So we're going to get anything from a radius of 0 to a radius of 10. But we really need to know how that radius changes as we go along. All right, well, here's what we're going to actually do. Let's put some axes on here. And let's see if we can start getting some equations and whatnot. So I'm going to start by just making it so that our cone has its tip at the origin. And it's going to come out this way. And then the other side is going to be down here. And then there's the circle that we get. Okay, so there's our cone. So first of all, let's think about the height of that cone. I tell you that the height is 10. So that means that if we're starting here at the origin, and that's 0, that means the very end of this is out here at x equals 10. Well, that's actually going to give us the bounds on the integral. We're going to take slices starting at 0, and we're going to keep slicing until we get out to 10. Now, to get the radius of the circle, let's look at one generic circle here. All right, so here's this guy. Its radius is actually going to be determined by the function itself. Right? As we move along this function, the radius is always determined by this function right there. So that means I'd love to have an equation for this line. Well, here's what I know. I know this point is the point 10, 10. How do I know that? How do I know that that's the point 10, 10? I mean, you can probably see why the x coordinate is 10, because that was out here. But why is the y coordinate 10?
The radius?
Yeah, it's from the radius, right? We're told that the radius, the big radius of the bottom here was 10, so that's the y value. All right, so I need the equation of a line that goes from 0, 0 to 10, 10. And hopefully it's pretty easy to see that it's y equals x. All right, so that tells me that my radius is actually equal to x. So this volume, it's going to be the integral from 0 to 10 of pi x squared dx. So again, that pi x squared, that was the cross-sectional area. That was the circle. The radius depends on what our x value is. The radius is x. And now we're going to get our volume. All right, well, if we do this real quick, the pi is a constant. The x becomes x cubed over 3. So we get pi times x cubed over 3 evaluated at 0 and 10. Plugging in 10 gives us 1,000 pi over 3. Plugging in 0 gives us 0. And there you go, ladies and gentlemen. There is the volume of that cone. So it all comes down to being able to recognize the cross-sectional area. Right? In this case, it's a circle. So we found the area of the circle, pi r squared, by figuring out the r. The r is determined by our function. And then we integrate. Okay, so this is exactly what I'm talking about. We're going to find volumes by slicing these things. All right, so to help you out, we're going to break these down into classes of shapes. Okay, the first one that we're going to look at, and this is kind of the primary one, is we're going to look at what we call a solid of revolution. And a cone is an example of a solid of revolution. So is a cylinder. So is a sphere. There are lots of things that are solids of revolution. But basically, all a solid of revolution is, this is a volume formed by revolving a function, or let's say a curve, about an axis. Okay, so a solid of revolution is anything that you get if you just take some curve and you spin it around an axis. So axis just means line, right? And so it doesn't have to be the x-axis, doesn't have to be the y-axis, just has to be a line. So if you ever can get this shape by taking a curve and spinning it around, that's what we call a solid of revolution. All right, so let me show you a generic solid of revolution so that we can kind of talk about how we build the integral to find the volume. So here's some coordinate axes, and let's just take a curve of some type, say this guy right here. So there's some sort of curve, and we're going to spin it around an axis. We can do this in lots of different ways, but let's start by spinning it around the x-axis. So if I were to take this and rotate it around, let's think about what this would look like. All right. So we're going to take this curve and we're going to spin it around so that we're going to get a circle over here. We're also going to get a circle, bigger circle from the other side. And we're going to get all kinds of intermediate circles. But basically what we're going to see down here is the mirror of the other guy. And this is the shape that we're going to see. So I don't know what that looks like. It kind of looks like a bowl to me, with the flat bottom if you turn your head sideways. But we're basically taking this curve and we're taking the region in that curve and forming a solid. All right, so technically what we're doing is we're taking what's called a planar region. So a planar region is just some area in the plane. We're rotating about an axis and we're getting a volume. Now, I have an example to show you, a physical example to show you of these as well. I am this kind of guy that when I'm out in the world, I see calculus everywhere. I see trig everywhere. I see physics everywhere. So I was at a friend's wedding decades ago now, and they had these centerpieces, and I went, oh my God, I got to have the centerpiece. Like, look at that, like, what? I was like, no, I got to have this because this is calculus. This is a volume of revolution, solid revolution. Like, what? Yeah, check this out. Okay, so here is the planar region. Kind of looks like an airplane, right? Got your tail here. Now what I'm going to do is I'm going to rotate it about this axis. All right, so I'm just going to start rotating it. And I'm going to keep going until I go all the way around in a circle. All right, so I'm back to where I started. And notice that I now have a three-dimensional shape. That's a bell. Right? So here's another solid of revolution that came from rotating this planar region about an axis. So I know you've seen these kinds of things before. There are tons of them out there. Those are all solids of revolution. And if you want to find its volume, you just have to figure out the cross-sectional area. Okay, well, check it out though. The cross-sectional area, they're circles. They're always circles if it's a solid of revolution, because we're spinning this thing around an axis, it's making a circle. So let's think about how we find those areas. All right, well, the area is a circle, which means we need pi r squared. And the thing about this radius is that radius changes with the function, and it's exactly f of x. It's exactly f of x. Yes, you're exactly right, Rigney, that you do create in art, ceramicists, that's a fun word to say, do also create solids of revolution. You can also create them with lathes. So if anybody's a woodworker and you use a lathe, you're creating solids of revolution. There are lots of them out there in the real world. All right, so it turns out since the radius is just given by the function, here's how you calculate that volume. You're going to integrate from A to B. So let's just say that this is A and this is B. And what you're going to integrate is pi times f of x squared dx. And that's always the case when you've got a solid of revolution. So if you come back to this example with the wedding bell, I just noticed, I just chuckled because there's still a price tag on it. 85 cents. And it was probably a wedding about 25 years ago, which means these are probably now what, like $4 a piece or something. Yeah. All right, so if I wanted to actually calculate this volume, I would just need to be able to describe this outer thing as a function. If I can write an f of x for this, I put it into this formula right here, and I know A to B, I can get that volume. So this is one reason we love solids of revolution, is because their cross sections are circular. And circles are really easy to do. Right? So this one would be revolving this region about the x-axis. All right, but what if we instead did it around the y-axis? So I'm going to erase all this green stuff. But let's think about revolving around the x-axis, so or y-axis. So same deal. Except now it's going to look like that. And of course, the cross sections are still all circles. But now the radius isn't determined by f of x. Right? It's not the vertical distance anymore, it's the horizontal distance. And so in that case, the r is g of y. It's kind of like when we were looking earlier at those turn ourselves sideways to calculate areas. If we turn ourselves sideways here and think about this, then this is a function of y, and that's what gives us our radius. So this one would be a volume from A to B of pi times g of y squared dy. So we have to change it to a y because we're looking at slices that are going vertical as opposed to horizontal. But it's exactly the same structure. All right, so let me do one. Let's take a shape and we're going to rotate it both about the x-axis and about the y-axis. So you can see that we get a different volume because it's a different shape. Like, look at this shape compared to the other one. This is definitely a bowl shape. And it's going to have a different volume. We're going to be able to fit a different amount of cereal in it for breakfast than the other one. Right? So it definitely matters which way we're revolving. All right, so let's go nice and easy. Let's take y equals x squared. We like that one. Let's take y equals x squared. And we're going to go from the point 0, 0 to 1, 1. Okay, so we're just going to look at that portion of it. And A, we're going to revolve it about the x-axis. And then we're also going to revolve it about the y-axis. So we'll figure out those two volumes, see those two shapes and what their volumes are, so we can compare them. All right, so here we go. We're going from 0, 0 to 1, 1 on y equals x squared. So there's that piece right there. All right, so let's start with the revolving it about the x-axis. So my shorthand for this, I'm just going to draw like a little circle that's got an arrowy thing in it around one of the axes. So I'm saying, hey, let's spin it around the x-axis. So that means we're going to use this purple formula over here. We're going to integrate from a to b of pi f of x quantity squared. All right, so about the x-axis, this shape, which is going to look like that, I guess kind of looks like a rose thorn, maybe. That's the way I could describe that. But let's see what the volume of that shape is. So that volume is going to equal the integral from 0 to 1 of pi times x squared squared. Right? Y equals x squared is the function. F of x equals x squared. So we want to take f of x and square it. So x squared squared. So this is the integral from 0 to 1 of pi x to the 4th. The pi is a constant multiple. X to the 4th becomes x to the 5th over 5. We're going to plug in 1 and we're going to plug in 0 using the fundamental theorem. And that ends up giving us pi over 5. So the volume of that shape, of that solid, is going to be pi over 5 cubic whatevers. Cubic inches, cubic feet, cubic meters, cubic light years, whatever. All right, so easy enough, right? Go about the x-axis, we're done. Now, if we're going to go about the y-axis, it's not really that different. We just now need to think about what are our y bounds and what is this thing as a function of y. So now this is going to give us a different shape, right? That's going to give us like a bowl. So one way we get a thorn, the other way we get a bowl. But if we go about the y-axis, this is what it's going to look like. We're still going to integrate from 0 to 1 because the y values are 0 to 1. But now we need to have a different function that we're squaring. I'm not going to put in x squared because that's that function as a function of x. If I want it as a function of y, I have to take this equation and actually solve it for x. So if I just take a square root, I get that x is equal to the square root of y. And that's what's going to go in there. So it's exactly the same curve. X equals the square root of y is the same curve as y equals x squared. But we need it with y as the variable. All right, so this is going to be the integral of pi times y. So again, pi is a constant multiple. Y becomes y squared over 2. And that one, we get its volume is pi over 2. So it's a very different volume. It's quite a bit bigger. It's 2.5 times larger. But that's because we get a different shape since we're revolving it around a different axis. All right. So if you want to revolve it around the y-axis or x-axis, the only difference is whether we're using a function of y or a function of x. But either way, it's going to be pi r squared. Okay, so this is a good place to pause. And we'll come back to this. We will definitely do more volumes by slicing because there's a lot more I got to show you. So on Friday, here's our plan for Friday. So Friday is quiz day, right? Quiz day like always. So at 8:30, go ahead and dive in and get your quiz. We'll start class at 9:10. The quiz, because I know everybody's dying to know, is going to be on 1.6 through 2.1. So 1.6 was integrals that involve logs and exponents. 1.7 were integrals that involve inverse trig. And then 2.1, that's the area between curves stuff. All right, so that's what's going to be on the quiz on Friday. So you're going to do that. At 9:10, we're going to be back in here, and we'll do some more volume by slices, and maybe we'll get to volumes by shells. I'm not very optimistic, but anyway, so that's where we are. We're in the middle of section 2.2, just so you know if you're playing along. So with that, I'm going to go ahead and stop our recording, and I will see everybody on Friday. All right, so have a great couple days.
Thank you,